Hello everyone, for this tutorial video I like to explain L'Hopital's rule, and also give the proof of it as an explanation of why you can only use it in the scenarios you can use it in. If we first assume that function at point A equals function 2 at point A, or g of point A, equals 0 exactly, then we can deduce that function at arbitrary point x equals function of x minus function of point A, and do the same exact logic for function 2 or g of x. So now we take the limit as x approaches a of the ratio of these functions, rewrite the functions with what we just assumed, divide the functions by a common factor of x minus a, and now we can break the limit into a quotient of two limits by basic properties of limits. And these limits are exactly the derivatives of the functions. In conclusion, provided that function at point A and function 2 or g of x at point A both equal 0, the limit as x approaches a of the ratio of these functions is exactly equal to the ratio of the derivatives of these functions. The proof of L'Hopital's rule for infinite or negative infinite limits is, we write capital L as a shorthand for the limit as x approaches a of function of x over g of x. And we assume that in this case, both f of x and g of x approach either infinity or negative infinity as x approaches a. But it is important that the overall limit, capital L, is not infinite, nor should it be 0. Only the individual terms can be infinity or negative infinity. So now, using basic properties of fractions, we can rewrite the limit like so. And we see, because these terms go to 0, as g of x and f of x go to either infinity or negative infinity, we can use the form of L'Hopital's rule for 0 over 0. Use the quotient rule and chain rule as appropriate. Flip the fractions back. Break the fraction into two separate fractions, and use capital L for what we defined earlier as a shorthand of the first limit. So now we are in the final steps of our proof. If we assume that as x approaches infinity, there is a limit of function of x over g of x, then we can define a substitution of t equals 1 over x, and take t approaches 0 from the right of the function in g of 1 over t. Apply L'Hopital's rule to this. Use the chain rule and quotient rule, then simplify it using traditional algebra tricks. And lastly, convert back from t to x. We should conclude that as x approaches infinity, the limit of function of x over g of x is exactly equal to the limit of the derivatives, which is what we wanted to prove. So now that I have proven L'Hopital's rule exhaustively, we can take the limits of specific functions using this tool. For example, the limit of sine of x over x as x approaches 0 we know to be 1 because we use trigonometry to find out. But if we use L'Hopital's rule, we get cosine of x over 1 equals 1 over 1 equals 1. So either method works and you should get the same result. Which should make logical sense. If you have the same limit point asked for the same function, your answer should not change. You can also use L'Hopital's rule more than once because of how it is specifically defined. For example, if we take the limit as x approaches infinity of e to the power of x over x squared, if we just try using the normal L'Hopital's rule, we have e to the power of x over 2x, which is still infinity over infinity. But when we take L'Hopital's rule again, we get e to the power of x over 2, which is simply infinity, because infinity divided by a finite number, as long as it's not 0, is simply infinity. We can also use methods we used earlier, for problems outside of L'Hopital's rule, to rewrite functions into something we can use L'Hopital's rule for, such as this limit, because we know 1 over x is simply x. So we can rewrite this as ln of x divided by 1 over x. Then use L'Hopital's rule, and we see it simplifies algebraically to negative x. And as negative x approaches 0 from either the left or right, it doesn't matter, the limit equals 0. If we have this limit, we cannot use quotients directly, like we could in the previous example, but we can use logarithms. So we take the ln of both sides and rewrite the right hand side using the properties of logarithms. And we see that it simplifies to a quotient, which we want for L'Hopital's rule, so we apply L'Hopital's rule now. But this is not our final answer, as we must remember we took the logarithm of the argument and not the actual argument itself. So we remember, if we raise e to the power of ln of y, we get y. So we can use this identity to rewrite the limit asked. And see, because e does not depend on y or any variable, it is a constant, we can put the limit inside the e, and we proved earlier that as x approaches infinity, ln of y equals 0. So we plug this in, and in conclusion, the limit asked in the beginning of the problem is e raised to the power of 0 equals 1, so that is the value of the limit. Now that I've explained why L'Hopital's rule works the way it does, as well as situations you could use it in, I can talk about a more common and not as obscure application of derivatives, which is known as linear approximation, because you are using a tangent line to approximate the value of a function, which can be used to simplify complicated calculations, which engineers often have to do all the time. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.